Okay, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. Most of you know me, but my name is Francesco Petruccione. And this afternoon, I have the pleasure of introducing Professor Martin Bucher, or Bucher, how it's called on radio. Now, we advertised Martin's talk on the Stellenbosch radio, student radio, and MFM, Mattis FM. So, and there he was known as Martin Bucher. But anyway, is he the same person?
He pronounced your name.
Yeah, yeah,
Excellent.
yeah. But he practiced a few times already. Okay, Martin is based in Paris, where he works at the CNRS. And physically, he's based in the Université Paris Cité, I think. Yeah. But he's also linked to Stellenbosch University. And in fact, he has a fractional appointment in the School of Data Science and Computational Thinking. And he's also a NITheCS associate. Yeah? Martin is also a member of the South African Academy of Sciences. Yeah? And has a long tradition of being linked to various South African university, but I will mention only Stellenbosch, not to mention the competition. So Martin, we are very happy that you are here and that you spend some time with us in Stellenbosch, and you're most welcome to start with your presentation. Thank you very much. Yeah. And sorry, but just one thing that I always forget. The rules of the game are always the same. For those people online, you're welcome to raise your hand or write a question in the Q&A, and we will come back to you at the end of the talk. Thank you very much. Thank you, Martin.
Okay. Well, thanks for inviting me. And I was going to talk about two topics that are sort of in the future of the CMP, which is kind of an old subject. So one is better observations of the frequency spectrum in the, sort of range of frequencies where most of the photons are. And that's something that has to be done from space and is very expensive. And then I was also going to talk about lower frequencies. So this is the Rayleigh jeans part of the spectrum and what you can learn from that. So the first is, learning about the very early universe at times before recombination, which is where the universe became transparent. And then the latter is one of the big questions is when did the first stars and quasars form? And the talk is also going to be a combination of theory and experimental technique. So that's where the word absolute measurement comes, because absolute measurements are much harder to make than relative measurements. So yeah, so this is the outline of the talk. And I'll start here with plot of the, so this is in microns, millionths of a meter. So you can see there in frequency, there's, almost 20 orders of magnitude. And then this is the intensity. And in astronomy, you generally want to look at many different frequencies to, get the maximum amount of information. And, what you're sensitive to different things at different frequencies. So I'll sort of use this plot to, introduce the subject. So the radio is, a highly non-thermal spectrum, and this is, cosmic rays, mainly cosmic rays whizzing around in magnetic fields. And so this is sort of SKA physics. Then when we go to, centimeter and millimeter wavelengths, we get a near perfect blackbody. And so these are the remnants of the Big Bang. At higher frequencies, here you see a different peak. So this is the cosmic infrared background. Yeah, so cosmic microwave background, Big Bang, cosmic radio wave background. So this is from dust at about 20 Kelvin. Then you get stars. So this is a UV optical, and then X-rays and gamma rays. So we're mostly going to talk about this part and go in this direction. So let's see. Yeah, so the history, I will go rather quick through the first slides because this is, sort of more familiar, but I sort of want to set the stage. So this is slightly older than I am. This is the horn antenna where Penzias and Wilson at Bell Labs discovered the microwave background, and they noticed that it was almost isotropic at different parts of the sky, same temperature, and consistent with a black body. So this had immense implications because this falsified these steady state models of the universe and really showed, unless you were a conspiracy theorist, that, the microwave photons at least were at thermal equilibrium and came from everywhere. To put this in perspective, so here's this thermal history of the universe. So we have an expanding universe, and we sort of start at the Planck era, and as the universe expands, it cools down, and when it's a couple thousand degrees, you no longer have a plasma, you have atomic hydrogen, and then this radiation goes to us, and now it's microwaves. And so we get this sort of snapshot of the universe at this epoch. And, this is slightly old. The universe is a bit younger, but you have this sphere that's around 45 billion light years in diameter, and you get this picture of what things look like. We're later going to talk about the sort of an intermediate era where, the first stars are formed, and that's something we know very little about. So we more or less know these initial conditions, what things were like at this epoch. We know less, we have the inflationary cosmology, and it's all very satisfying to theorists, but it's not so well tested. Okay. So what do you see? So I take this slide as almost 30 years fast forward. And so this is when I entered the field, when COBE discovered the anisotropies in the microwave background. So here you have, if we looked at the microwave temperature of the sky and we used a sort of normal color scale, it would look almost completely uniform. Then we subtract away the monopole and we see this dipole. But you know that if you're moving, then the Doppler effect is going to give you this well, almost perfect dipole. So you can see the galaxy here, and then they subtracted this away. And these are, you can see the galaxy and the equator, but these fluctuations, follow a blackbody spectrum. So this field of looking at the difference in temperatures is, greatly advanced. And I'll just show a few summary slides because this has, been the story of the last 20 years or so, better and better measurements of the anisotropy. And it's sort of interesting. COBE also measured the absolute frequency spectrum, and that stands as the best measurement today. There hasn't been any improvement on it because one has to go to space, and I will explain why a bit better. Okay, I'll just mention the Planck satellite. So this is for looking at differences in temperature. Is the sound's working? So this is about the size of a car, and it spins around, and you have these beams that are looking at the sky, and these are the detectors. So these are micro. They have very good directional properties. So you sort of don't want to see the back of your instrument. And then there are these detectors that are bolometers. So they're at about a tenth of a Kelvin, and that they get heated up with by the radiation. So these are very unstable. You don't really know the 0 point for longer than 5 seconds. So you're comparing different points in the sky. You're not measuring, with respect to an absolute reference. And then you see these maps. So this is the frequency in gigahertz from 30 to 857. And you see the galaxy is the least visible in these sort of intermediate frequencies. Here you have radio emission. And if we would go to lower frequencies, this would take over, from our galaxy. And then at higher frequencies, there's this dust that, here you just see the dust and you don't see any microwave background. So you can take linear combinations, and, this is more visual. The data analysis is not done exactly in this way, but you can see the galaxy is not visible anymore. And then, this can be analyzed in various ways. So this is basically in the predominant theory based on inflation, Gaussian noise. So, we scan and we record lots and lots of differences, and we make these maps. So that this is how it works. And then Gaussian noise is characterized by a power spectrum, and you have these sort of oscillations. So this is sort of sound that, they're all set. All the modes are sort of set at the same phase at the Big Bang, and you can see them oscillate. And, then from the shapes, get the parameters, and then the, bottom plot, which is the difference between the best fit model. So this is a little like trying to read patterns in the coffee grounds, well, maybe there's a dip here, but by and large, you don't really see patterns here. So that shows that that's a pretty good fit to the inflationary theory. And then here we see the polarization, both in cross correlation with the temperature and, the autocorrelation. And I'll show this plot. The green is what you just get from the polarization. The red is the temperature and everything combined. And you can see that you get a consistent story. In other words, the temperature and the polarization corroborate each other. So that sort of tells you that you're on the right track. Okay, so I just wanted to show these slides because this is sort of the mainstream, CMB measurements, and it's becoming a mature field, except for maybe the polarization and the gravity waves. But here you see the so this is from COBE FIRAS, the spectrum, and the error bars are thinner than this line. So this really places very severe constraints and deviations from this hot Big Bang. And this is something that in the future, if people are willing to, pay the money to have a dedicated satellite. I mean, there's been a lot of improvement in technology. One can do much better than this. And let me just tell you what deviations one might expect to be able to see. So suppose there were a lot of explosions in the early universe, and these explosions are sort of shrouded, behind the plasma. So there's a large optical depth. The direction of the photons gets randomized. Well, their energy and the number of photons, the energy doesn't get redistributed that quickly because you have heavy electrons and not so energetic photons, so there's hardly any recoil. And then the number of photons through three-body processes got sort of equilibrated with the temperature when the universe was a millionth of its present size. So the microwave photons come from Z, redshift Z is equal to 1,000. So you would see spectral distortions. So that's one thing you could see, that there's some, high stakes discoveries. The other thing that you might see is when the hydrogen, which is ionized, recombines to become neutral hydrogen, then in this tail you see, you will see these recombination lines, and then are there heights as expected. So there are spectral distortions, which with proposed instruments can be detected. Okay, we're in the slide with the sky maps I showed you. Well, this is the CMB anisotropy, and then we have these foreground synchrotron, which is the cosmic radio background, and that the temperature goes up and up as the frequency goes down, and the same with the dust. So we'll talk a bit about looking at spectral distortions at in the 100 or so megahertz range, in the physics that you can get from that. Okay, so let me first talk about the low frequency distortions. So 21 centimeters is the wavelength that we'll be looking at, and I will tell you why in a second. And then that gets redshifted. So basically, wavelengths longer than this allow you to see at a variety of redshifts. And the physics behind it is the 21 centimeter hyperfine transition of atomic hydrogen. So not molecular hydrogen. It has to be atomic and not ionized. And the F is the total angular momentum. So you have the nucleus and the electron, and they can either be aligned or disaligned. So you get this, well, I guess it's a two-level system, with four different states. And if this temperature associated with it is hotter than the blackbody, which is behind it, you will see an excess of radiation as opposed to a blackbody. And likewise, if it's colder, you will see an absorption feature. So this is the physics, and there's a temperature that you can measure. And when we talk about global, we're talking about the average. In other words, we're not trying to look at objects. So you get a stronger signal, but it's harder to measure because you need to make an absolute measurement. So these are the predictions that so here we have frequency, and this would go to whatever 1400 megahertz, and basically what you have happen here is the first stars form. So that's what cosmic dawn is, and then they make ionizing radiation, and eventually all of the atomic hydrogen gets reionized, and you have the universe as it is today. So we're at the non-redshifted 1450 megahertz. So let me go through this. Some of it is rather straightforward. So why does the temperature of the spin system go down? Well, when you have non-relativistic particles, their kinetic energy goes as p squared. So it redshifts is 1 over the square of the expansion factor rather than 1 over the expansion factor. So the atomic hydrogen is cooling down, and the collisions between the kinetic temperature and the spin temperature that create a tight coupling, and then as the gas becomes more tenuous, that sort of breaks down and it heats up again. And then there's something that I will explain on a future slide called the Wuthuysen field effect, which, you would think that having ultraviolet photons would heat up the spin degree of freedom, but at first it does exactly the opposite. And then, as there's more energy, everything heats up, so you get this pattern. So you're trying to map this out. So this might be less interesting because, we sort of think we know the physics behind it and can model it, even though it would be satisfying to verify that we're on the right track. But here, we don't know from the first stars and quasars how much ionizing radiation there is. And the more there is, the, deeper this trough and the earlier. So you can learn something about astrophysics that you cannot model because, star formation is complicated, it's linear, there are magnetic fields and all sorts of stuff. So people can try to model it, but we don't really know. So that would give us some new clues. So the ultimate goal would be to, map this whole thing out. So let me explain to you the Wuthuysen field effect. And this is kind of surprising because we have these two spin levels, upper and lower, and they couple through the of an electron volt. So you would think that this difference wouldn't make any, would be completely unobservable. But then when we look at the rate equations, what we see is that, if we look for a steady state, the population of the upper and the lower level is related to, this, the population of the photons. So that's in the upper state. And so the this is not really the photon temperature. It's how the temperature varies with energy. And then you get something similar for, the Doppler splitting. So the uh, uh, um, velocities of these neutral atoms moves this around. So you get a coupling between the kinetic temperature, which has a high heat capacity, and there are hardly any Lyman alpha photons. So these photons basically couple the spin temperature to the kinetic temperature. So that's why you get this downturn. Okay. So there has been a flame detection of this within a number of years ago with this experiment in Australia, and I'll show you a picture of it in a second. And they claim to see this huge absorption feature, which is much larger than what you would any theory predicts. So here's the EDGES antenna, and this looks like a table, and this is a very desolate part of Australia, so there's virtually no radio interference, and there's some chicken wire on the ground to try to create a ground plane. So the dipole antenna basically looks in all directions. And here are the results from their Nature paper. So the first thing you see is, from our galaxy, there's this very smooth spectrum with a, brightness temperature at the lowest frequency of 5,000 degrees. And this gets fitted away. So the argument is that this should be super smooth, and then you subtract away, and you get this absorption feature, and it's about 2 to 3 times. This is a fit, about 2 to 3 times of what is expected. So there have been tons of papers about why, what might have been gone wrong, trying to reanalyze, and there are a number of experiments. But basically nobody, there's no conclusion yet. So this is a number of sort of a Monte Carlo of simulations, and you can see that, well, first of all, the blue kind of fills a large area. So the theory is not very predictive, but, the size of the trough is, way deeper than what any of these models can predict. So here you have, these are a whole bunch of experiments. Saras is an Indian experiment, and they haven't seen anything. They have an antenna in a lake that where the water creates a ground plane. REACH is a Stellenbosch Cambridge experiment that I'm part of. So I will, take the liberty of telling you a little more about that experiment. Okay. I think I will go through these slides a little faster so I can, so this is about techniques and with measuring the anisotropies. And here, this is a radio receiver from WMAP, and they switch between these two antennas, and at about 3 kilohertz, I think, and the beam is split through, 2 amplifiers. So both go through the amplifiers, and then or switched between 2 detectors. So you only measure with this phase shift the difference between the two, and the amplifier instability cancels out with this configuration. So you're just measuring differences in the sky, and you make a map out of that. The bolometric detectors are more stable. So this is the noise of the detector, and you can see it, after about 5 seconds, you get this low frequency excess noise, and the 0 point isn't stable. So you're moving the beam, and you filter out the, low frequency signal, which is just all noise. So this is how anisotropy experiments work. I'm going to skip some of these slides with the details. It's interesting, but I really want to, get to reach. Let's see. Yeah, these are tricks for the anisotropy experiments. So first, what does FIRAS do with this problem of the instability? Well, the idea is if you want to test that something is, excellent blackbody, and you don't have a stable measuring device, the one thing you can do is build a better blackbody, and then just look at differences. So we have this Fourier transform spectrometer, and they're these, wire grid beam splitters that actually split the polarization, and you got both polarizations, and then you change the path length, and then the path length steers the signal between, the calibrator, the perfect artificial blackbody in the sky, and the in the actual sky, and this is the data, this difference. So how do you make a better blackbody than you think the microwave background is? Well, it's a bit like, in a recording studio, you want to not have reflections off the walls. So you want to create this perfect absorber. So these are spikes of some sort of epoxy with metal material, and they create a dissipative refractive index, which outside is, the same as space, and then you get complete absorption. Or if you want to think about it at higher frequencies, if you have a narrow wedge, and then you have the smaller the opening angle, the more reflections you get. So if you have, say, 20 reflections, there are many opportunities for there to be absorption. So you can actually build an artificial blackbody. So this is from the NASA Goddard Space Flight Center. This is for a successor mission that has been proposed but not approved to FIRAS called PIXI. And hopefully something like this will get approved. So let's see. The REACH experiment is a successor to the EDGES experiment. And this is the Nature article that describes the experiment and the strategy, and how they plan to do better than EDGES. So this is in the Karoo near the SKA site. These are not towns, these are really farms, and the closest town is Carnarvon, which is almost an hour's drive away. And it's very desolate. So this is the bar in Carnarvon, and you can see they haven't updated the photo of the British monarch yet. Okay, so the antenna is, this is the first REACH antenna, which is similar to, there are two metal plates and then a ground plane. And here you see there are these sort of spikes that apodize the ground plane so that there isn't any sort of hard refraction. So one of the challenges is that, this is just, maybe 7 wavelengths across. So there's a lot of diffraction, and eventually part of the beam is going to hit the ground and see all of this stuff up here. So everything has to be modeled, and that's a formidable challenge. So what REACH is going to do when it's fully deployed is there's going to be a second antenna, which is a helical antenna. So it's a little like a wire wrapped around a Christmas tree. And that is a lot more directed. So that has the advantage of avoiding the ground, and also, the galaxy is basically ring that, since it's a plane cutting the celestial sphere, you're always going to see it to some extent. Maybe it will be at the horizon, but if you can have a more directed beam straight up, then you have less of the galaxy, and you get more finely grained data. So this is taking data now, but not really scientific data. It's being debugged. So this was for a more specialized conference. So this was sort of a quiz question. Does this calibration work? So the answer will be no, but basically the idea is that, we look at the sky with this antenna, and then we have a noisy amplifier, and we don't know what its gain is or how much noise it has. So we just measure the power out. So you take a cold load, a hot load, and the sky, and I got this out of some paper, and it's actually, you can make a plausible argument that there's just the noise, the gain, and then get the antenna temperature. But this will not give you the right answer, and the reason is that noise is more complicated. You have 4 real parameters, and that describe the noise. There's a current source, a voltage source, and then they have correlations, and then you have 6 unknowns. There's the amplifier, there's the sky temperature. So if you have 4 equations and 6 unknowns, you can't solve it. And the reason is that these antennas have a rather complicated impedance pattern, so it'll never be the same. So the thing in the previous, there's disagreement, surprisingly, with some of the formalisms, about how to calibrate the instrument, which should be just straightforward electrical engineering. Okay, so this is a schematic of the reach instrument, and basically you have the antenna on the sky, you have the amplifier, and then you have all these different resistors and impedances, which allow you to characterize the noise. And then there's a vector network analyzer built in, and it characterizes all of the electrical parameters, and they're mechanical switches that switch back and forth. So there's a lot of redundancy, and that should allow one to get the temperature very accurately of what's coming in. The antenna pattern is a problem I won't talk about. It's another big problem, the chromaticity of the antenna, that you have a different beam at different temperature frequencies, and that needs to be corrected for. I'll skip this. This is some work on the calibration, and let's see. This is something I will just mention that I think is sort of related and kind of interesting from metrology. So we know that for almost 100 years that resistors are noise sources, and there's this formula about the relation between the voltage fluctuations and the resistance, or the real part of the impedance. So in metrology, there's been a tendency to get rid of the standard meter as an artifact, to get rid of the kilogram and everything. And for K. Boltzmann, using Johnson noise, it's further down in this abstract. You can measure K. Boltzmann to 5 times 10 to the minus 6. So this isn't the most accurate, but this is basically the calibration principle, being used to try to make a comparison for these types of measurements. So I guess the conclusions are, for astrophysics, that measuring this spin temperature is a function of redshift. It's going to really give us a lot of constraints about part of cosmic history that we can't at present probe very well by other means. This is complementary to experiments such as HERA's also in the Karoo Hyrax that look at the 21 centimeter line, but look at inhomogeneity. So how does the temperature from point to point differ? So the signal is smaller, but since they're just looking at differences, this is in some sense, an easier measurement. The reach type of edges experiment is difficult because you have this galactic foreground that is a lot hotter than the blackbody that you're looking at distortions of. So you can't play this game of making an artificial blackbody. You have to more make an absolute measurement. So it'll be interesting to, see what the result of this is. The edges is sort of set a challenge to theorists. Can people come up with models that explain this kind of observation? So it pushes theory on the one hand, and it creates an incentive for people to do other experiments and check and really see if there's some sort of surprise out there. But even if it's wrong, I mean, we saw these curves of models. If we did a really good measurement at a range of redshifts, we would be able to constrain the history of how the first objects in the universe formed. So I think that's one of the reasons why this is an experiment worth doing, perhaps with a higher budget. So thank you for your attention.
Thank you very much, Martin, for the great talk. Are there questions for Martin? Here comes the first question.
Thank you very much for this a very inspiring and clear talk. You discussed the distortions on the CMB due to hydrogen hyperfine lines coming from stars and quasars. What about the distortion? And you discussed them in the frequency spectrum. What about the effect of those phenomena on the polarization map of the CMB?
The that's a good question. The degree of polarization is not very large. The degree of if you look at Stokes parameters, you know, the signal that we're looking for is almost in the all in the I Stokes parameter, but the synchrotron radiation is highly polarized. So, you know, if we had a narrow frequency range, maybe 30%, because you see I mean, the physics of it is that, you know, it's the galactic magnetic field, and, you know, you would expect the cosmic ray distribution to be approximately isotropic. You know, there are lots of collisions, and, you know, so you got a very polarized signal. So one of the worries is that if you have a dipole antenna, not with the helical antennas, you just measure one linear polarization. And is that going to compromise your ability to, you know, remove that smooth spectrum? There's also Faraday rotation, which can be your friend. And that if you look at, you know, broad smooth over frequency, you know, something that twists a lot averages to 0, but then it puts on features that vary rapidly with frequency. And as I showed you with the edges plot, you know, we have this huge thing that starts at the thousands of degrees and falls like a polynomial. And we subtract that off, and then we're claiming that the, you know, feature of half a degree, that's a detection. So polarization from our galaxy could fool us.
Questions for Martin? Do we have any questions from the online audience? No? Okay, Martin, here we go.
Now that there is time. I have one more question. Can something be learned from these electromagnetic type of measurements? Can something be learned about the gravitational wave signal of the early universe?
Well, yeah, yes. So that is one of the frontiers with the, you know, CMB anisotropies. So if you, well, first of all, I mean, there's no uniform polarization, you know, because you can't, if you comb a sphere, I guess it's the Harry-Ball theorem, they're going to be 2 bald spots. But there's this decomposition into so-called E modes and B modes of the polarization. And an E mode is basically something where I can take some scalar potential on the celestial sphere, I take the gradient twice, I subtract out the trace, and then I get this sort of pattern of, double-headed arrows or axes that have different lengths. And if you have scalar perturbations, which are believed to be the only thing that creates matter perturbations, you just get the E mode. And the B mode is roughly excited in the same proportion, not exactly, by the gravitational waves. So if you find primordial B modes, then that's the sign of gravitational waves from inflation. So that's why people are willing to, the Japanese have a satellite called Lightbird that will measure the polarization, and testing inflation is a lot judged to be a lot more of a priority than checking FIRAS and looking for these explosions that may or may not be there. So yeah, you touched on one of the really interesting areas with microwave background and anisotropies.
Thank you.
If there are no more questions, my pleasant duty. Thank you on behalf of all of us, the little NITheCS sponsored mathematical magazine. So
Okay,
thank you very much.
you.
Thank you very much.